Train faster or train steadier. Pick mini batch or full batch. By the end, you will see a tiny Python trainer in action. Measure mean squared error before and after updates, and compare speed versus stability in numbers. You will understand when a single sample update helps and when a full dataset step is safer. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. In practice, you choose between full batch and mini batch when you train models on real data. Full batch computes gradients across the entire dataset each step. It is steady and predictable, but can be slow and memory heavy for large datasets. Mini batch samples a subset each step. It is faster per update and often generalizes well, but the updates are noisy and can jump around. Success means reducing error reliably while keeping training time within your budget. Think of training as walking down a hill to the lowest point. Full batch looks at the whole landscape each time and moves smoothly. Mini batch looks through a window and sometimes takes bolder steps, which can speed progress but risk missteps. On a small toy line that follows y equals 2x plus 1, full batch gives clean, precise updates. Mini batch gives faster but jumpier progress. Both can reach the same place if you tune learning rate and batch size. We will build a tiny linear regression walkthrough that prints mean squared error at key steps so you can hear the trade-offs before we compare updates numerically. Now we'll compute a full batch baseline. This snippet computes the baseline mean squared error on a toy linear dataset where 2 points follow y equals 2x plus 1. This example sets parameters w and b to 0 to represent an untrained model. It forms the residuals by subtracting targets from predictions, squares those residuals, and averages them using NumPy mean, which computes the average across values. The code then rounds that result to 2 decimals, so the number is compact and easy to read. The printed mean squared error of 5.0 becomes our simple stability baseline before any training. Next, we will step once using the full dataset and watch the error change. This example performs a single full batch gradient descent step and reports the new mean squared error. It computes residuals over both samples and builds gradients by averaging those residuals. Then shifts the slope and intercept by a value scaled by the learning rate. The learning rate controls how far parameters move each step. Make it larger to speed progress but risk overshooting, or smaller to improve steady convergence at the cost of speed. After the parameter update, the mean squared error is recomputed to show the immediate improvement from a full dataset stable step. Now we'll compare gradient sizes between full batch and a single sample mini batch. This code compares the size of gradients from the whole dataset with those from a single sample mini batch. It first computes the full dataset residuals and their average gradient for slope and intercept. Then it picks one sample and builds a single sample gradient. To summarize the 2-component gradients in a single number, it uses NumPy hypit, which returns the Euclidean norm of its inputs and effectively measures the gradient magnitude. Larger magnitudes usually indicate jumpier, noisier updates in stochastic steps, while smaller magnitudes signal smoother moves from full batch computation. The printed pair makes that contrast clear numerically. Next, we will run one mini batch epoch that updates per sample and observe the result. This snippet runs one epoch of stochastic gradient descent by updating parameters per sample, and then computes the resulting mean squared error. It copies the parameters so earlier results remain available, then loops through each sample, computing the residual for that sample and applying a per sample update immediately. Because each update uses less data, steps can be faster and target specific errors quickly. But they also introduce noise compared to the averaged full batch step. The final mean squared error summarizes how much the model improved after processing both samples once with per sample updates. Finally, we'll repeat tiny mini batch passes from scratch to see cumulative progress. This code runs 3 full passes of per sample updates, starting from 0, to show cumulative mini-batch learning on the toy set. It initializes slope and intercept at 0, then iterates the sample list 6 times, so each sample is used 3 times. Using a moderate learning rate of 0.25, balances steady progress with reduced overshooting on this tiny dataset. Increasing that rate would move faster but risk instability, while lowering it would require more passes. After the 3 passes, it computes mean squared error to summarize how well repeated mini-batch steps fit the linear pattern in the data. Recap in 3 crisp points. What it is: full batch averages gradients across all data for stable steps. Mini-batch updates on subsets for faster, noisier steps. When to use: choose full batch for tiny datasets or when stability matters. Choose mini-batch for larger datasets or faster iteration. One caveat: mini-batch noise can help escape shallow traps, but can also destabilize learning if the learning rate is too high. Next step: run the same experiment while tuning batch size and learning rate, or scale the dataset and measure wall time and error so you can see how speed and stability trade off in practice. If AI Foundations in Python help you, subscribe and watch the AI Foundations videos.